Hello my friends and welcome again to my video channel. Today we will continue our work on the R&S EK070 with the work on the power supply, where we have identified a problem. So let's start. The power supply unit is out, and the first thing which I have seen are these bridges, these additional wirings. I'm a little bit surprised about it. I thought it's a professional unit which does not have such okay, no comments, but the reason is rather simple. The integrated circuit which is located here is not the same as which is in the schematic. We have here a circuit. I will show it to you. This is B2 in the original version. It's a 723, but inserted is the MC33.2, and the MC33.2 is the same as the LM339. We know it's a quad op amp or comparator which is used for voltage regulations. The 3302 has a little bit less voltage range. The others have 36, and this has only 30 volt, but this is not, I think, not relevant in this design. The manufacturer of course thought about this, so this modification here is necessary due to other pin layout of this integrated circuit, and we can see it also on the other side that there are additional modifications not necessary to show. But we see here one problem which I think is not okay. The wiring from here to here is very close to this pin. From this pin to this pin we have the wiring, but here should be no connection. But this wiring here is close, very close to this pin. And also this wiring which goes from there to there is also very close to these two pins. And if there is a small fiber, metal fiber, or any solder blob, one of these small blobs which are sometimes generated when soldering, they can fall into these gaps here and make trouble. These would be troublemakers par excellence. I will try to make it a little bit better to avoid problems. This could be a problem, especially by transportation, some vibration, some squeezing the board. Temperature, humidity could also have an influence on it, so this is not a good practice. Mr. Rodi and Mr. Schwartz, what did you do there? Not good. Now there is sufficient space. I didn't use a new wiring. I only shifted a little bit up, heated the pin and squeezed up the wire with this ceramic trimmer. Did the same here, so we have now enough space between. Doesn't look good on the camera as I see, but it's better in the reality. So this topic cannot generate problems in the future. By the way, we see additional modifications with this integrated circuit due to the change of the type of the IC, of the quad op amp or quad comparator. So it's obviously a later version. Maybe in those times they had problem with buying these types of integrated circuits, same problems as we have today, so they had swapped to another design and modify something. Well, that's it. Next topic are the electrolytic capacitors. Now to the electrolytics, and I've seen that this electrolytic here is not the original one. This one has a pressure relief, this one has a pressure relief, but this one not. And this is rather loose, not fixed. This is fixed, and the other one also. The reason is, or we can see it on the bottom side, that the wobbling capacitor has only two pins, someone soldered in. The other two pins are not existing. These are for mechanical fixing, not electrically important, but mechanically. Here we have plus and minus. And we see, again, there was someone in. There's the other cap. All four are soldered, so this cap is fixed, and the other one also. You see here three, the fourth pin is under the metal sheet. This one is not original situation, and the value I've seen is only 10,000 microfarad. Can you see it? No, but I can tell it, 10,000 microfarad. And the original one, the original should have 22,000 microfarad. Okay, I'm not sure whether this is important. It's for the 5 volt rail, 5.3 volt rail. Maybe this is also sufficient to avoid ripple with a 2N30 55 in series to have sufficient output voltage. Now we will simply measure the capacities. This is C3, should have 10 millifarad. I'm measuring at 120 Hertz. We have here the plus and here is the minus. 10,000 microfarad. I'm measuring 347, and the quality, oh, it slipped off. Quality is .17. Looks not so nice. The next one, which is C2, should have 22 millifarad. We have seen there is 10 millifarad in it. We have here the minus, and this is the plus. Should be 10. And we have 9.3, quality 2.5. Okay. This is and the third one should be 4.7 millifarad. Okay, that's 4.8, quality is 4.5. We cannot expect much a bigger quality than 3, 4, 5 for these caps. So we can say one is okay. This one, which has been replaced, holds its values, but this one is out of spec. And an additional topic we can see when we look very close to the electrolytic cap, we can see here's some signs of leakage around this vent. So we can assume, can you see it? Focus here with the music. Yes, we can see it. There are some acid coming out. This is the cap which lost capacity. So we'll take it out. The capacitor is out. We measure 546. Should have 10,000 microfarad at 120 Hertz. Quality is .2. So this capacitor is definitely dead. This was the capacitor with the signs of leakage here in the vent. The other one, which has been replaced, is this one. Look for the plus and minus. Yes, it is minus. And here we have the plus. This should have 10,000. This seems to be okay. 9.4 millifarad. This is at 120 Hertz. When we measure at lower frequencies, we have 10,000 microfarad, quality 2.5. Okay, this capacitor could be accepted as okay, but I will replace it anyhow. And the third one is obviously okay, but I think I will also replace it. The power supply unit is out. The electronic board with the regulators is removed. We have here a plugged connection, so this unit can be easily removed. We will focus on this board later. The 3 electrolytics are out. I've looked for 3 new ones, and now we have a little problem because the old ones have 4 pins, and as we see here, and the relevant pins is always this pin and this pin. This is 10 millimeter, so the rest would be okay, but it is not centered, so this electrolytics would be shifted when we use the original pins for the capacity. So it's difficult here to get them in. My first thought was, okay, I will drill new holes in it, but the boards are rather crowded. Top and bottom layers are there. Only this capacitor here could be installed without big problems, but this one here, there are traces, and there are also traces, and even this one has a lot of traces on bottom, on top and bottom cover. So I need a sort of adapter between, and I have an idea what to do. The idea is to use a perforated board to make such an adapter, which is flipped over the pins. The hole has to be drilled a little bit, and here are the markings for the 4 pins, and we use a stiff wire to solder it to this and then bend it up here and here, so we have at the end 4 wires which fit into these holes. 2 are used for connection. For example, this one and this one is plus and minus. Plus, minus, and these 2 are not connected. They are free and they can be used as a mechanical support. So the big electrolytic is a little bit more stable and cannot flip around. This is the idea, and I will try it. The wire is soldered. Now we have the 4 pins, as you see, and when everything is okay, they should drop into the holes, and then they can be soldered more or less easy. Where is the problem? There's a problem. Wrong sequence. And now they fit. We only have to look for shorts on this side, that there is the pins are not shorting, and here they can be soldered. It's very important in these boards to look that the vias are okay when soldering. Otherwise there's a danger that the connections are not good when the vias are missing. When taking out the old electrolytics, I think I have the feeling that I took out 1 via. Yes, here it looks like that 1 via was taken out with the pin. This happens in these old boards, that the vias are not perfect, and when taking out the electrolytic, the big electrolytic, the vias are also taken out. They are ripped out. Not good. We have to consider that. All 3 electrolytics are in place. It's an advantage that there's a small gap between, because then we can solder also on top of the board, not also on the bottom side. It's necessary to solder some pins also on the top side where the trace is. This is valid for all 3 electrolytics. Now they are in. Next step is the electronic board, and I've seen that there have been some repair attempts made, especially on this side. You can see that there is something, some signs of soldering here also. Here we have a brown spot. This is a Zener diode which gets a little bit hot, 24 volt. It's the power supply for this integrated circuit. I will replace it by a new one and lift it a little bit from the board to have a better ventilation. One resistor, as I've seen here, is damaged. It was an external impact. Don't know what happened. There's also a sign of some smoke. It's not smoke, it's not overloaded. I think it was a drop of solder blob or some flux. The other electrolytics, for example, this one here is not the original one. It was swapped by a different value. I will take out all electrolytics. No discussion necessary. These are standard electrolytics. This unit deserves to get new electrolytics also in the electronic, in the power supply. Also these tantalums will be replaced by new ones. So we can say when it is installed again that we have completely replaced all electrolytics. Now we are prepared to swap the electrolytics and the Zener diode, as we can see here. I don't show it in steps, it's not necessary. You know how to swap capacitors. No big problem. I only want to show you a detail with respect to this diode. We can see here some signs of heating. Two small traces of dust caused by the heat inside this diode. This is Zener diode. The dissipated power is approximately 130 or 120 milliwatts. I calculated it roughly. I will measure it later. The current for this resistor here is something in the range of 5 milliamps. It's a series resistor for this Zener diode. So 5 milliamps times 24 volt is 120 milliwatts or so. Over the years, the heat got up. Additionally, there's also heat generated in this resistor. Same power loss. So both components are heated a little bit and made this trace upwards. It's not critical over the decades, no problem. They generate the base voltage for this transistor. This transistor is an emitter follower and is used to supply the integrated circuit here with 24 volt DC. I will raise this diode a little bit, use a bigger one. This has a nominal power of 500 milliwatts. Okay, it is efficient, but I will use these types, which are a little bit bigger. They have 1.3 watt nominal. Well, let's start. All electrolytic and tantalum caps are swapped. I also replaced the Zener diode. We had a discussion, and the series resistor 4.7K also. Both are lifted up a little bit from the board, so they are not flat on the board, as we can see here. They have a little bit of distance, some millimeters. Another question: how good or bad were the old caps which have been replaced? Let's measure it. The first one is one of the Fracos. Should have 100 microfarad. We have 120. Quality is 14.7. So I think it would be still okay. A little bit an overperformer, but I don't think that's a problem. It's within the tolerance. Important is the quality factor. It's very high. So this capacitor would be good for another 100 years or similar. Let's take this one. Should have 470. $515, quality more than 20, measured at 120 Hertz. When I go up to 1 kilohertz, the quality drops, of course. 470 microfarad still. That's okay. And the third Fraco should also have 470. 500 quality, also 17, 18. Well, they are okay, these old Fracos, but I'm lucky to have them replaced. Here we have the next ones. These yellow Röderstein should have 100 microfarad. And these old are ugly. 100 microfarad, 1 microfarad, and quality 0.3. Maybe this is more resistor. Maybe the DC resistance is nearly 0, the isolation. But 1 microfarad instead of 100 has to go. Third one, also 100 microfarad. 180 nanofarad. Quality .2. The next catastrophe, and the third one is this one. 8 nanofarad. These 3 caps are totally bad. Loss of capacity, and you may ask, how is it possible that the power supply worked? Well, these capacitors are not so important for the circuit. They have been here, and these capacitors are there on the output. Let's have a look into the diagram. They are on the output of the voltage regulators. This one is here 100 microfarad, this one, and maybe this one. So these are in the output of the voltage regulators. They are not so important. The stabilizing against oscillation is made here, and this one is only for reducing the noise. Hum is not a problem because hum is reduced by the regulator itself. So this capacitor is not so important, and when it fails, maybe the next capacitor, also here is one, maybe the next capacitor in the receiver in one of the modules also has an input capacitor and filters it out. So it's not a problem, but of course it's good now that they are replaced. The next candidate should have 470 microfarad. It's 455. It's one of the big filter caps. Okay, could be accepted. The other one has also, let me have a look at it, 400. Is it 470? Yes, 470 microfarad. The 15 quality is 8, it's the same. I think these 2 capacitors are also okay. Could have been tolerated for the next some years. Here we have some tantalum caps. This one should have 47 microfarad. And it has 44. Quality factor 56, 58. So I think this tantalum cap is still okay. Next one is a smaller one. It's 10 microfarad. Quality factor of 86. Wow, okay, 120 Hertz. Let's go to kilohertz. What does it say? 15. The quality drops, but still 10 microfarad. So this is also okay. The next one should have 47 microfarad again. And it is. At 1 kilohertz, 44, 45. When I go to 120 Hertz, 45, quality 66, 65. should have 47, 45. It's okay. Yes, 1 microfarad quality factor 100. Whew. Whew. And this one is 10 microfarad. So we can say all tantalums are still perfect. 10 microfarad, quality 50. And the last one I have here is 220. This was in place of one of the 100 microfarad electrolytics. Someone swapped it. One of these maybe have been replaced. Should have 220. And we have 250. Okay. Okay, quality 6. At 1 kilohertz. Maybe this one is bad. Well, the big ones we have already seen. One was bad with the leakage. What can we say? 3 of the electrolytics are completely dead. One of them is not so good. And this one is also bad. Sorry about this one. So we can say these are the bad ones and the other ones are all good. Except this one, I would say this tantalum is also bad, 220 microfarad. So this one was necessary to swap and the other ones are acceptable. But I'm not sure when the receiver is operating for some hours whether it still stays okay. So it wasn't wrong to swap all the electrolytics in the power supply. The board is reinstalled. The power supply is ready now. It's connected to the power source, 230 volt from my isolation variac, and running for several hours. And now we can check the output voltages, which are on this connector here, on this pin. And we have several voltages. I don't show you everything, but for example, the 5 volt, the pin 1 is the 0 volt, and pin 14 and 15 is minus 5 volt. That's okay. And 7, 8 and 9 is plus 5.3. That's okay. Then we can check the 12 volt. This is 29. 29 is minus. Other way around. 29 is minus. And 31 should be 12 volt. 11.92, that's okay. And we have 14 volt. 4 is the negative. And 11, 12 is plus 13.95. Should be 14 volt plus minus 1%. 1%, sorry. 1% is 0.14 volt. Yes, we are within tolerance. That's okay. And now I've promised you to check the voltage drop across the Zener diode and the resistor. We have it here. What is what? Sorry, the diode is this one. No voltage. 24.5 and the resistor has 24.6. Okay, now we can calculate 24.6 volt over the resistor. 24.6 divided 4.7. We have a current of 5 milliamps times 25 volt is 130 milliwatt. Same is valid for the Zener diode, because we can assume that the current in the Zener diode is the same as in the resistor, because the base current into the transistor, which is connected to the Zener diode, is very low. We can assume a rather high beta. So it is a power loss of 130 milliwatt in the Zener diode and in the resistor. Totally 260. This is an explanation why we had, after some years of operation, a little bit of decolorization of the board. Well, that's it. Next step is I will bring this unit back into the receiver. We bring it back in the same way as we took it out. This is a mechanism of the switch. It should be blocked. 1 moment, let's block it, yes. Here are 2 pins, concentric pins, and then the unit can be dropped in. Is it so easy? It is easy. There are no tolerances. Ha! That's okay. I love it. The receiver works again, as we had before. And now the big question, what do we do with the other electrolytic caps inside all these modules? The front panel, there are also, I assume, some electrolytic or tantalum caps on it. I will have a look into the parts list, whether the bad electrolytics I found in the power supply, I'm talking about these ones, these yellow types, you remember, they had a total loss of capacity, whether such types are also installed in the other modules. I can check it with the parts list and with the number or the designation of the component. Each component has an individual number, so I can check whether such capacitors are also in the other modules. This will be my first check now. Now we are at the end of part 2 of our videos about the Rohde & Schwarz EK070. I talked to the owner how to proceed, and we agreed to do a little bit more effort because this receiver deserves it. It's a very unique piece of technology from those days, and we shouldn't hesitate to invest some time and also some money, of course. Again, it deserves it. What we agreed, you will see in the next video, in part 3. Stay healthy, stay tuned. See you on this channel.